Okay, so limits. We're going to take two approaches to this initially. First of all, the concept of limits is going to make you uncomfortable because it's probably not like anything you've done before, but I'll go slow and try not to use big words. We're going to do it numerically and we're going to do it graphically. I find graphically much, much easier, and so I'll show you a couple pictures, and hopefully the picture will help you make sense of what we're going to be doing also numerically. All right, so you should be able to find the limit using a numerical and a graphical approach. You should understand what happens when you can't take a limit. You'll see that in a couple of minutes. There'll be a breakdown in trying to take the limit. You need to know how to handle that. We're going to skip the formal definition of the limit right now. We're going to do an informal definition and a mechanical definition, meaning how do you go about doing it. We're going to skip the formal definition right now for this simple fact that it will melt your brain. And the first day in calculus, I don't want people running out of their rooms crying, heading downstairs to see the dog. Okay, so we'll come back to the formal definition later. You don't really need the formal definition. It's not in the AB syllabus, but it is an important concept and a fairly theoretical idea that you should be introduced to at some point in time. So when we get to those slides, I'll just have you close your eyes and we'll go right past them so that you don't have flashbacks. Okay, so limits. First question is, what is a limit? Our informal definition is the following. A limit is the y value that a function approaches as you get close to an x value or a given x value. Shall I say that again?
Yes.
It's a y value that the function approaches as you get close to some x value. Okay, so for instance, let's take this. We'll make that at -1. So we'll say that this is f of x, and we're defining f of x as 2x minus 1. Okay, simple line. The limit goes something like this. Let's pick a point. Oh, I don't know, 3. What's the limit? Well, I don't want to use that word. Hold on. What's the value of the function as I get really close to 3? And this seems like a silly question. Why are you asking us that? You'll understand why in a minute. As I get really close to 3, okay, in other words, I'm traveling this way, but I'm staying along the function, I'm going to get closer and closer to this point right there. What is that point?
5.
I'm sorry?
5.
5, right.
I was like, am I wrong?
No, I just didn't hear you, that's all.
Okay.
5. If I approach from the right, what if I come from the left?
5.
5. Any problems with that? That seems stupid, doesn't it? Why can't I just put 5 in there? 2 times 5 is, or sorry, 2 times 3 is 6, minus 1 is 5. Easy, right? Why do you all look confused?
Because it's not going to be easy.
It's not going to be easy, but if you understand this,
Yeah.
what we're going to do will be a lot easier.
Okay.
Okay. As we get closer and closer to 3, what is the value of the function getting closer and closer to? So if I stop out here at 3.1, I'm going to be up here at some value, which is getting closer and closer to 5. The biggest thing that freaks people out about limits is we're not necessarily going to talk about what's the value at the point. We're going to talk about what happens as you get close to the point. And how close are we talking? We're talking really close.
Hecka close.
Like 0.0000000, infinite number of zeros, 1. Okay. But initially when we start with something easy like this, it's actually approaching the value of the function. Okay, that went better than expected. Let's try this. Rational function. Does anybody have any idea what that looks like? Good, because if you did, I'd worry about you. Like the other function that we just erased, what's the first thing we should do?
Graph.
No. Yeah, solve it. Plug in 4. Oh, I forgot to talk about the notation here. This means what is the limit as x gets really close to 4. So the first thing you should do is plug in 4, see what happens. Don't be bashful, get out your calculators. Question?
When it says with that notation, does it mean as you approach point from both sides of the graph?
And we'll talk a little bit more about that as we move through through the lesson.
So,
Wait.
Oh,
Okay, what do you got? Not 0. Say you, Josh? Why is it undefined?
oh, whoops, I forgot.
First thing you have to remember about limits, you always try every single limit problem, I don't care how complicated or easy it is, by plugging and chugging. Because it might be as simple as that linear equation we did initially. The value of the limit as it gets really close could be just the value of the function. This one, however, doesn't work because as Josh mentioned, we get 0 over 0. What's 0 over 0 equal, by the way?
it's
One.
yeah,
Could be
it
1.
could be
Why?
one.
John, is it 1?
Well, because the same number over itself is 1, but it could also be 0.
It could also be 0 because,
0, anything divided by 0, or 0 divided by anything is 0.
good, and the third thing?
Undefined.
Undefined because we have a 0 in the denominator. So which one is it?
I don't know.
Correct. Okay. We don't know what that means, and we won't talk about that again until probably March.
That's good.
But what you need to know is that's bad. We don't like that. 0 over 0 causes all kinds of problems. Okay, so that didn't work. And that could happen. It might not happen. In other words, if you plugged in a number, if you plugged in 4 and you just spit out a number, then we'd be good to go. We're done, let's move on. But this one didn't work. What are we trying now? I'm sorry? So you, no,
I said 4.1.
you could try 4.1 and then what?
3.9.
And then what?
Keep going and going and going and going and going.
4.0.
4.01 and then
4.00.
4.001 and then 4.0001 and then look for a pattern and see if it's getting closer to some value. Good, that's coming up later. What else?
3 point.
Yeah, go on the other side and do 3.9999999. Okay. Any other ideas? Which is a valid method, but we'll come to that later. I'm sorry? Graphic. Right. And again, I have no idea what that looks like, but another approach would be to figure out what it looks like, use your calculator to graph it, which we're not gonna do. Okay, that's a second method. So try a bunch of numbers that get close, graph it. Any other ideas? You have 2 quadratics, what can you do with a quadratic? Factor. Go ahead, try it, see what happens. Maybe something magical will happen. Or maybe not, it'll just be a train wreck and we try something else.
Oh, wait, oh, something.
Oh man.
I think I have a little problem with your socks. I can remember one of the Ninja Turtles having an orange headband.
It was my
I thought it was red, blue, yellow, and
No
red,
yellow, blue.
no yellow.
Yeah, no yellow.
Orange.
Oh, it was red, blue, orange, and purple.
Purple.
Purple. It's after my time, but I was actually around when the Ninja Turtles were just a comic book. Some guy printed in his basement and made $1 billion off them.
Sounds like such a stupid thing if you think about it.
Making $1 billion?
No, no, the
Oh,
Ninja Turtles.
printing a
with the
comic book with some
turtles
turtles in
and
it,
the
yeah.
ninjas.
Who would have thought? Crazy. All right, what'd you find out?
That I can factor the first one. one on top.
Congratulations.
Thank you. I'm proud. I know, I don't know what I'm doing here
I'll
either.
let that one go, I don't know where to go from there. What else did we find out? Right.
You can cancel out x minus 4.
Beautiful. If you factor it correctly, you have an x minus 4 on the top and an x minus 4 on the bottom, so we get to that. Okay, now, how does the x minus 4 canceling affect the graph?
There's a hole as well.
There's a hole, correct. Okay? So now we have a function with a hole, and where is that hole?
X plus 4.
At x equals 4. Now there's a problem though, because we're looking for what happens at 4. So as I get closer and closer to the function, unlike the other one we did where there's a value there, there is no value here. So the graph looks something like this. And I have no idea if it looks like that, but you get the general idea. I can get closer and closer to 4 coming in this direction. I can get closer and closer to 4 in that direction, but I'm never going to hit 4. So how do I figure out what the value of the function is if there is no value at the function?
What?
Did that not make sense?
No.
What's the value of the function or the value of the limit as you get close to a number that's not there? And that's the key to limits. We don't care what the value at the function is. We care about what happens when you get really close to that point. The easiest method that we get to is that after you've tried plugging and chugging and it doesn't work, and then you algebraically manipulate it, also known as factoring it, and you cancel things. Question?
So when we have a limit, there's always going to be like a hole or something like that, or no?
There's usually going to be 3 scenarios. Like the first one where there's just a value, and that's why you try plug and chug first. You'll get a hole, that's going to cause some problems, or you're going to get an asymptote.
How can you have a limit if there's already a value there though?
Because it's still getting close to that value as you get closer and closer to it.
Okay.
Okay?
Okay. Yeah.
So if I'm trying to get to a point over there, as I get closer to it, whether or not there's a value there doesn't matter because I'm still getting closer to it and I'm getting close to the value that's at that point.
Okay.
Factored it, canceled some things out, we realize there's a hole in the graph, can't figure out the value of the hole in the graph, so let's pretend the hole isn't there and plug and chug again. If we plug and chug again, we get the answer of 15/17. So what I did is I cheated the system. I said, well, the x minus 4 is canceled, that generates a hole in the original graph. Well, let's pretend the hole isn't there. What would the value of the function be? Well, the value of the function would be this value of 15/17. Remember, this is the y value that you're approaching. For those of you that are graphical learners, we have a picture, and let me explain not only the notation, but also the graph of what's going on here. So we talked about the limit notation already. I'm taking the limit as x approaches a, some number a, of the function, and when we do that, we get a y value, which is referred to as capital L, stands for the limit. Graphically speaking, here's what's happening. We have some curve, or some graph, and we're getting closer and closer to a as we move along the graph, which means we're going to get closer and closer to this y value, which we refer to as L. And we can talk about coming from the left and coming from the right. That's what we're going to do next. In general, does that make sense? Good. It might not, but that's okay. It'll start to fit together in a little bit. So again, plug and chug first. If plug and chug doesn't work, then try to algebraically manipulate it. In other words, cancel. Then plug and chug again. If that doesn't work, then we need to come up with a different method. And those different methods we'll get to in a second. Okay. So let's look at a new function. 1 over x. One of your mother functions. What's it look like?
There's explicit x and y intercepts.
Beautiful. Looks like that. So what happens as I approach this function, for this function, what happens when I approach 0? What does the value do? And remember, limit is defined as the y value. So what happens to the y value as I get closer to 0? It approaches infinity.
I think so.
Explain that to us.
Well, since if you plug in a really small value underneath 1, you get a really large number, and as that number gets smaller that you plug in, you get a larger number as a
Okay,
result.
good. So there's a numerical approach to it. Plug in numbers that get very close to 0, the values get very big, because if the denominator gets very small, a fraction gets very large. Graphically speaking,
Wait, what?
as the denominator
Okay,
gets
it's
very
small. Yeah, okay, I thought you said the other thing. Oh, right, never mind. I'm good.
Okay.
I misheard him.
Okay, you're good. As I approach from the right-hand side, I'm getting closer and closer to 0, but the y value is going higher and higher and higher. We good?
Yep.
What happens if I come over from the other side, though? That's not going to infinity, is it? Negative infinity. So now we need to introduce some new terminology and some new notation. I want to be able to make a distinction between coming from the right or coming from the left. It looks something like this. What's the limit as x approaches 0 from the positive side of the function? Okay, plus means from the positive direction. We define this already as being infinity. What's the limit as x approaches 0 from the negative side of that function? And what did we say that was? Negative infinity. Third thing, what happens when you approach it from neither or both directions? What do you think?
There's no sign. There's no sign.
How do you approach something from
Yeah, but how do you do, for one thing, how do you do that?
Well, you can think of it as approaching from no direction or approaching from both directions, or just the value at the function. What's the limit at 0?
No solution.
Undefined.
No solution. Good. We refer to that as does not exist, DNE. Basic theorem involved in limits is the following. Have you got this? Can I?
Yeah.
Okay. I'll bring it back in a second. That's the fancy calculus speak, which is saying that the value of the limit at that point only exists if the value from the left-hand side matches the value from the right-hand side, which is what that says. Right-hand limit must match left-hand limit. If it doesn't, there's no limit. So the earlier one that we did that involved the rational functions, if I approach from the left or from the right, I'm approaching the whole, and the value would be the same. This one has different values. So therefore, the limit at the point doesn't exist. It still has a left-hand limit, still has a right-hand limit, but the value at the function does not exist. This is really important. Go
So
ahead.
it has a limit, it's just x at 0 does not exist.
Correct. Of the 3 possible limits, for this case, 2 of them work, the third one does not.
Okay.
Okay?
Mm-hmm.
And I'll do a couple more examples to make sure you get that. Anybody confused yet?
Yes.
Okay, what are you confused about?
What's the third limit?
The third is when you don't have a direction like this.
So it's just like,
What's the limit at that point?
isn't it always, I don't get it, isn't the point always like not there? Isn't it always like there isn't a point there?
Not always. Like, let's say, for instance, what is,
Oh, okay.
what's the limit as x approaches 4 of 1 over x? 1/4, right. This is just a plug and chug. First thing you always check is plug and chug. Can I plug 4 in there? Yep, I'm good to go. It's 1/4, which makes sense. If I come over here at 4, I'm at that point. Doesn't matter if I come from the right or from the left, I'm going to get that value.
So would the limit be 1/4?
Bad day to sleep through the lesson, dude. You might want to wake yourself up. You're going to have a horrible weekend. Okay? So understand the difference between the two. The other one at 0 happens when you have spots where weirdness is happening. There's a hole, there's an asymptote, there's something that's not normal. This is normal, it's fine, it doesn't matter. Okay, this not so normal.
So the limit would be 1/4 for that one.
Yeah, done. Plug and chug, get a value,
Yeah.
you're finished, move on.
I,
Okay?
So then if you don't get a value, then you have to like do the rest of the stuff, or?
Correct. If you don't get a value, by not getting a value meaning you get something bizarre,
Yeah.
0 over 0, something over 0, then you try to algebraically manipulate it, try to cancel things, try to do some other stuff, and then plug and chug again. If it doesn't work, then you're kind of out of luck.
So you only have to like continue if you don't get like a normal value,
Correct.
but then if you get the normal value, that's just the answer?
Right.
Okay.
And the two differences are going to be, if you get a normal value right away, you're here. If you don't get a normal value, you're here or at a hole. Next question.
I was just gonna ask, like with the whole, the value of the limit for the whole was what would be there, right?
You got it.
So then, it's just with the asymptotes that there's not actually a limit?
Correct.
Okay.
And I'm kind of jumping the gun here and talking about infinity. I think you all understand these, right? The idea of infinity and negative infinity. Technically speaking, from a pure calculus approach, this is not valid because they don't accept infinity as an answer because it's a concept, not a numerical value. But that's getting kind of nerdy, and I didn't think we needed to go here because I think that demonstrated what we needed out of it more so than the whole argument about whether or not infinity is acceptable. Okay, so let's look at this one now. Another example. That is not a parabola, but if you remember how to factor cubics, right, let's pretend you remember how to factor cubics, then the x minus 1s would cancel and we would be left with a parabola, and there would be a hole at 1 because that would cancel. So we're looking at a similar problem than what we had before. Okay. So that's what our function looks like. So this isn't much different than the rational one we did before, but it illustrates what's happening as you get close to that hole in the graph. So, like Mitchell said before, you want to basically look at what would the value of the function be if there were a hole, if the hole were filled in. Because again, I can't put 1 into the function, it doesn't work. So as I come from the right, I get closer and closer to
1 comma
no.
3.
3, right, because we're looking for the y value. As I come from the left, or from the negative direction, I approach 3. Does the left-hand side match the right-hand side? So what's the limit at 1? 3. That one works. So the previous one with the asymptote didn't work because the left-hand side didn't match the right-hand side. This one works because the right-hand side matches the left-hand side, and therefore the limit is the same as it would from the left and the right.
How would you figure this out if you didn't have, like a graph to look at?
Great question. Can I answer your question in a slide or two? Good. We talked about that already, and we got that already. Good. Okay, yeah, Okay, so this guy. I don't even know what to do with that function. But I do know that if I look at the limit there when x approaches 0, the first thing I should do is plug and chug, and when I put 0 in there for x, I get 0 over 0. That's bad. I have no idea what the graph looks like. I don't have my calculator. I've got to figure out some way to determine what the limit is as I approach very close to 0. And we talked about this new method earlier, and that is do something like this. Make a chart. And what that chart is doing is demonstrating what's happening as I get closer to the value from the left and from the right. And notice how exact it's getting, going from 0.01 to 0.001 to 0.0001. Looking at the numbers at the bottom, though, you can tell what is it approaching? 2. Does that answer your question, Kirsten?
Mm-hmm. So just like kind of plug and check type thing.
Right. But you want to be sure we're talking about very small values. So if you're looking at what's the limit at 0, you don't want to plug in 0.1 or 1. It's got to be really close.
You want to plug in what's closest to the limit that you're
Yeah,
trying.
and especially with a calculator where you can plug and chug.
So for these kind of things, we'll have our calculator or.
Yeah, when you're doing numerical stuff like that, I'm not going to expect you to be able to plug 0.0001 into it. That would be barbaric. Okay? So we can look at the graph and determine the limit from the graph. We can manipulate it algebraically. and find the limit. We can try plugging and chugging numbers into the graph. That's 3 possibilities for finding that limit. Well, actually, the 4th one is plug and chug. And then, again, for those of you that are graphically minded, that's what that function looks like. And you can see again from the picture what happens as you get close to 0. You're getting closer and closer to the number 2, which confirms what we had in the numerical chart on the previous slide.
And so for the last one, you could just be like, okay, limit equals 2, even though it doesn't, you can't actually like say it, but
Right.
it doesn't.
And that's what a lot of people get hung up on, is they don't understand how the limit, if the function has no value at the limit, how can it, if the function has no value at the point, how can it have a limit at the point? Well, again, we're talking about what happens when you get very close to the point, not what happens at the point. Okay, sometimes they're the same thing. The original line problem that I did, it's the same thing. It approaches the same value. But then when a hole is generated, now we can't figure out what the value is at the point. We have to look at when you get very close.
So you can't say like y equals 2, you have to say the limit.
Correct. The
is-
limit equals 2.
Yeah, okay.
Okay, now what happens when it doesn't work? And we hinted at this already. What happens when you get 0 over 0? This popped up on a homework problem in chapter 0 and I kind of glanced over it. This is a mother function that you should know. This absolute value of x over x graphs into a nice pretty picture like that. Okay? So there's a horizontal line from 1 extending to the right, and there's a horizontal line from -1 extending to the left. Okay, so let's ask a couple questions about this thing. Whoops. Itchy trigger finger. What is the limit as x approaches 1 of the absolute, well, you know what, I'll just do f of x, of f of x.
Well, why'd you change it to x approaches 1?
Hmm?
Why'd you change it to x approaches 1?
Because I'm just looking at an example first.
So it's not that one?
No, it's not that one.
Oh, okay.
What is it?
1,
1. Why?
because you plug in 1 to true value of x over
Perfect.
x, so 1 over 1 is 1.
Good. Start with a plug and chug, plug it in, okay? Or graphically, what happens at 1? Well, I got a value there, so it's just 1. What happens when you look at the limit as you approach x from the direction? So let's do it from the positive direction first. Go ahead.
When you do it from the positive, like when you do directions, do you have to have a graph for that?
No, but it helps. Because you can see on this graph, if I'm coming from the positive direction, what am I getting closer and closer to?
So how would you know if you only had like the values?
Then you could try plugging in numbers.
So you would plug in,
0.001, because it's getting really close to, it's a positive value getting really close to 0.
so what if it was negative, you just do a point negative?
Mhm.
Okay.
Okay, so what's this?
1,
Why? Because as I approach from the right, I'm getting closer and closer to, and in fact, it already has the value of 1. What is this? Limit as x approaches 0 from the negative direction.
1.
Which one?
1.
No,
Negative.
-1, because it's down here, approaching from the left. Therefore, what's this? You could all read, can't you?
It doesn't exist.
Does not exist. That's why it doesn't exist. And the question I'm going to ask you is, why doesn't it exist? And you're going to tell me the left-hand limit does not match the right-hand limit. That must be true in order to have a limit at the point. So notice I have a right-hand limit that works, I have a left-hand limit that works, but now all of a sudden the limit itself at the point has no value because they're different. If they match, you're good to go. All three work, everybody's happy. If the two left hand and right hand don't match, then you have no limit at the point. Okay. And that just summarizes, oh, okay, don't look at any of this stuff.
Oh, God.
Don't, look away, kids. This is ugly, scary. Okay. Oh yeah, no, okay, we'll stop there, okay. We're gonna skip over that, because some of you will start to cry. So this summarizes what you're gonna do. When you get into this homework, it's a completely foreign concept to some, well, to many of you, to all of you, and you could get fairly frustrated. You gotta stick with it, because this is a basic foundation of calculus, and as I've described before, we're taking a bunch of puzzle pieces and fitting them together. Eventually we'll have a nice pretty picture, but until then we just got a bunch of puzzle pieces laying around. This is a pretty important puzzle piece. It's like the corner. Anybody do jigsaw puzzles, you know what I'm talking about? Okay, just checking. You said no. Have you ever done a jigsaw puzzle? Okay, so you know what I'm talking about. Yeah. So this is an important piece. And then we're eventually gonna fit them all together, and when we're done, we have this pretty picture about calculus. But this stuff is gonna be fairly foreign when you start doing it, but you gotta remember some of the stuff we talked about in the slideshow, the difference between the left-hand limit, right-hand limit, and the value at the function. That summarizes, I actually forgot to include cry in there.
Yeah, I was thinking about that.
That would probably go,
First,
Before prayer, I think.
number one.
No.
probably
But you
before
just gotta-
starting the homework.
Yeah.
Gotta get it out first.
You just,
Exactly.
like a cleansing?
Yeah.
exactly.
Okay,
Yeah.
so 0.5 should say cry.
Yeah.
And once you've had a good cry, then you can plug and chug, algebraically simplified, look at the graph, guess, pray, and plug and chug again.
You can do it again if you want.
No, pet the dog I think would come after,
After the whole thing.
I think 6 points, or 7 would be pet the dog.
Seven.
After all of that doesn't work, then you go to the dog. Or maybe it would be,
Sleep.
7 would be cry, then 8 would be pet the dog.
Or both
One-
at the same
or
time.
both.
0.5
Yeah.
and 7 is cry.
You wanna bookend it with crying? That's a lot of crying.
And someone in the
That's
middle
how it
too,
went.
to be honest. Maybe you should
Well,
tell us to
plugging
do
and
that
chugging
before we
your
begin
number
class. Okay.
Maybe it should just be
1 through
inclusive.
6, cry.
Cry
Everything,
every
or
time.
cry with everything.
Like if you had soaks your mouth on with tears, you're not doing it right.
Me every day.
0.5 is start to cry and continue to cry until complete, and then get to the bottom. Or it'd be like 1.5, C.5, 2.5, C.5, just keep going.
I'll just like stare before you guys.
Yes, excellent. Mitchell had a great point, make sure you drink a lot of water to stay
Yeah, I was gonna
hydrated.
say
All
that.
that crying, you could get dehydrated, and next thing you know, you're in the hospital.
Calculus is dangerous.
What, dehydration?
No calculus.
Calculus is
It
dangerous.
could, yes. It's risky.
Calculus kills.
Calculus.
It's like for the
Not
exams.
yet.
Yeah.
Not yet. As far as my students go, I haven't had any students die from calculus yet.
Yeah.
Yeah.
That's rare.
I have had priors.
It's like laughing.
It happens all the time. You'll see later, probably about January, after first semester, we'll take a survey, and I'm guessing it's usually about 75% will admit to crying at some point.
Has anyone?
By the way, that's guys and girls, so some of you guys will cry too. There's nothing to be ashamed about it. I cry all the time. It's okay. No judgment. We're a judgment-free zone here.
Do you cry over calculus?
Do I cry over calculus? Oh,
Like
no.
they'll be just.
Tears of joy.
Do you like it?
Huh?
You like it?
Do I like calculus? Oh, I do it for a living.
Yeah, but do you like it?
I mean, do I go home am I gonna sit at home over the weekend and do calculus
Like,
problems
I'm
just
pretty
for
sure
fun?
Mr.
No.
Brett.
That sounds
Pretty
fun.
sure
I
It's
know,
not a
I
hobby.
like
It's a job.
It's a
I'm still recording, aren't I?
Have
So I
fun
need
with
to
that.
Like if anyone missed this, they can